There are several possible causes for GFCI breakers tripping when lab equipment is started. Firstly, consider a line neutral reversal. Check if the line and neutral wires are connected correctly at the panel and receptacles. A reversed connection can cause nuisance tripping. Secondly, a ground fault could be occurring somewhere in the circuit or equipment that's causing the GFCI breaker to trip. Check for damaged wires, loose connections, or faulty equipment. Thirdly, multiple single-phase circuits in the same conduit can create capacitive coupling between the circuits, which could cause nuisance tripping of the GFCI breaker. Fourthly, the GFCI breaker itself could be defective or have a low trip threshold. Try replacing the GFCI breaker with a new one. Here are some troubleshooting steps you can take. 1. Double-check wiring connections. Confirm that the line, neutral, and ground wires are connected correctly at the panel and receptacles. Use a voltage tester to verify. 2. Isolate ground faults. Disconnect the equipment and test the circuit with a GFCI receptacle. If the GFCI receptacle does not trip, it indicates a ground fault in the equipment. 3. Test for capacitive coupling. Turn off all but one circuit in the conduit. If the GFCI breaker trips when the single circuit is turned on, it suggests capacitive coupling. Consider using separate conduits for each circuit. 4. Replace the GFCI breaker. If all other troubleshooting steps fail, try replacing the GFCI breaker with a new one. Use a GFCI breaker with a higher trip threshold if possible. 5. Contact the manufacturer. If the issue persists, contact the manufacturer of the GFCI breaker or the equipment to discuss possible solutions. It's recommended that you use a licensed electrician for all electrical work to ensure proper installation. Regularly test GFCI breakers and receptacles to ensure they are functioning correctly. Consider using class A GFCI breakers, which are less prone to nuisance tripping due to capacitive coupling. Provide clear labeling for each circuit at the panel and receptacles to facilitate troubleshooting. To further elaborate on line neutral reversal, it's important to understand the proper wiring configuration. In a standard 120-volt circuit, the black wire is the hot or line wire, the white wire is the neutral wire, and the green or bare copper wire is the ground wire. The hot wire carries the current to the load, while the neutral wire returns the current back to the source. A GFCI breaker monitors the current flow between the hot and neutral wires. If there is an imbalance, indicating that some of the current is flowing through an unintended path, such as a person, the GFCI breaker will trip, cutting off the power. If the line and neutral wires are reversed, the GFCI breaker may not function properly and can cause nuisance tripping. Use a multimeter or voltage tester to verify the correct wiring. At the receptacle, the smaller slot is for the hot wire, the larger slot is for the neutral wire, and the round hole is for the ground wire. At the panel, the hot wire should be connected to the breaker, the neutral wire to the neutral bus bar, and the ground wire to the ground bus bar. Regarding ground faults, these can occur due to several reasons. Damaged insulation on wires can expose the conductors, allowing current to leak to ground. Loose connections can also create a path for current to flow to ground. Faulty equipment, such as a centrifuge, may have internal components that are not properly grounded, causing current to leak to ground. To isolate ground faults, systematically disconnect each piece of equipment connected to the circuit and test the circuit with the GFCI receptacle after each disconnection. This will help identify the specific piece of equipment that is causing the ground fault. Once the faulty equipment is identified, it should be repaired or replaced. With respect to capacitive coupling, this phenomenon occurs when multiple circuits are run in close proximity to each other, such as in the same conduit. The conductors in each circuit act as plates of a capacitor, and the insulation between the conductors acts as a dielectric. When the circuits are energized, a small amount of current can flow between the circuits due to capacitive coupling. This current is typically very small, but it can be enough to cause a GFCI breaker to trip, especially if the GFCI breaker has a low trip threshold. To test for capacitive coupling, turn off all but one circuit in the conduit. If the GFCI breaker trips when the single circuit is turned on, it suggests that capacitive coupling is present. Consider using separate conduits for each circuit to reduce capacitive coupling. Another option is to use shielded cables, which can help to block the capacitive coupling effect. If the GFCI breaker itself is faulty, it may trip even when there is no actual ground fault or capacitive coupling. GFCI breakers have a limited lifespan and can become defective over time. A faulty GFCI breaker may have a low trip threshold, meaning that it trips at a lower current level than it is supposed to. To determine if the GFCI breaker is faulty, replace it with a new one. Be sure to use the GFCI breaker with the same voltage and current rating as the original breaker. If the new GFCI breaker does not trip, then the original breaker was likely faulty. When replacing the GFCI breaker, consider using a class A GFCI breaker, which is less prone to nuisance tripping due to capacitive coupling. Class A GFCI breakers have a higher trip threshold than standard GFCI breakers. The National Electrical Code, or NEC, provides guidelines for the installation and use of GFCI protection. NEC Section 210.8 specifies where GFCI protection is required. This section includes areas such as bathrooms, kitchens, and outdoor locations. NEC Section 406.4d specifies the requirements for replacing receptacles with GFCI protection. It's important to consult the latest edition of the NEC for the most up-to-date information on GFCI requirements. In addition to the troubleshooting steps mentioned earlier, there are other steps you can take to help prevent GFCI tripping. Ensure that all electrical connections are tight and secure. Loose connections can create a path for current to flow to ground. Use high-quality wiring in connectors. Cheap wiring in connectors can be more prone to damage and corrosion, which can lead to ground faults. Avoid overloading circuits. Overloaded circuits can generate heat, which can damage wiring and insulation, leading to ground faults. Regularly inspect electrical equipment for damage. Damaged equipment should be repaired or replaced immediately. Keep electrical equipment clean and dry. Moisture and dirt can create a path for current to flow to ground. Educate users on the proper use of electrical equipment. Improper use of electrical equipment can lead to damage and ground faults. Implement a preventative maintenance program for electrical systems. A preventative maintenance program can help identify and correct potential problems before they lead to GFCI tripping. When selecting a GFCI breaker, consider the trip threshold. Standard GFCI breakers have a trip threshold of 5 mA. Class A GFCI breakers have a higher trip threshold, which makes them less prone to nuisance tripping. However, Class A GFCI breakers may not provide as much protection against electrocution. Choose a GFCI breaker with a trip threshold that is appropriate for the application. It's also important to consider the voltage and current rating of the GFCI breaker. The GFCI breaker should have the same voltage and current rating as the circuit it is protecting. Using a GFCI breaker with a lower voltage or current rating can be dangerous. When installing a GFCI breaker, follow the manufacturer's instructions carefully. Incorrect installation can damage the GFCI breaker or render it ineffective. Be sure to test the GFCI breaker after installation to ensure that it is functioning properly. The test button on the GFCI breaker should cause it to trip. If the GFCI breaker does not trip when the test button is pressed, it is not functioning properly and should be replaced. Furthermore, when troubleshooting GFCI tripping issues, consider the type of equipment being used. Some equipment, such as variable frequency drives, can generate harmonic currents that can cause GFCI breakers to trip. Harmonic currents are currents that have frequencies that are multiples of the fundamental frequency of the power system, which is typically 60 Hz. These harmonic currents can create noise in the electrical system, which can interfere with the operation of the GFCI breaker. If you suspect that harmonic currents are causing the GFCI tripping, you can use a harmonic analyzer to measure the harmonic content of the current. If the harmonic content is high, you may need to install harmonic filters to reduce the harmonic currents. Another factor to consider is the length of the circuit. Long circuits can have higher impedance, which can reduce the effectiveness of the GFCI protection. The NEC specifies maximum circuit lengths for various wire sizes and voltage drops. Be sure to comply with the NEC requirements for circuit length. Additionally, consider the ambient temperature. GFCI breakers are designed to operate within a certain temperature range. If the ambient temperature is too high or too low, the GFCI breaker may not function properly. The manufacturer's specifications will indicate the operating temperature range of the GFCI breaker. If the GFCI breaker is installed in an area with extreme temperatures, you may need to provide additional ventilation or insulation. Proper grounding is also essential for GFCI protection. The grounding system provides a low impedance path for fault current to flow back to the source, which helps to ensure that the GFCI breaker will trip quickly in the event of a ground fault. The grounding system should be properly installed and maintained in accordance with the NEC requirements. The ground wire should be connected to the equipment grounding conductor and to the grounding electrode system. In summary, troubleshooting GFCI tripping issues requires a systematic approach. Start by identifying the possible causes, such as line neutral reversals, ground faults, capacitive coupling, and faulty breakers. Then, follow the troubleshooting steps outlined above to isolate the cause of the tripping. Remember to use a licensed electrician for all electrical work to ensure proper installation and safety. Regular testing and maintenance of GFCI breakers and receptacles are essential to ensure that they are functioning properly and providing the intended protection. Consider using Class A GFCI breakers in applications where nuisance tripping is a concern. Provide clear labeling for each circuit at the panel and receptacles to facilitate troubleshooting. By following these recommendations, you can help prevent GFCI tripping issues and ensure the safety of electrical systems. Also remember to consult with the equipment manufacturer for solutions if it continues after all of these steps. The manufacturer may have seen something similar and have recommendations as well. All electrical installations must follow local and national codes, and you should always consult with a qualified electrician.